for those last couple problems, you have if you got to them. All right, so don't spend 5 more hours tonight for 2 points. It's probably not worth it. You've got other things you need to do, and that's okay. All right, you're not expected to get 100% on everything. All right, so my suggestion is, if you've got all of the last 2 done, scan your documents, turn it in, move on. Okay? Unless you just have a couple more hours and it's just really bugging you and you really want to figure them out and get them. Which for some of you, that's okay. It's a more challenging problem. That's good. When you guys use a document scanner, when you scan the first page, if there's more than one page, flip the page and scan the second page. Don't turn in 6 files. Turn in one PDF with all 6 pages in it. If you don't know what I'm talking about, here at the end when we have some time, ask me and I'll show you, okay? So you can put them all together in one document. It's a lot more efficient to upload and it's a lot more efficient to grade. All right, so we're going to move on and talk about a new idea. Quickly review what I think you know. If you graph position versus time, the slope is the velocity. I know you know that because, except for the 3 of you that can't spell velocity, you all got it on the warm-up, right? 4 of you missed this one. Again, acceleration. I mean, the word velocity was in the next line. It said, where's the slope of a velocity versus time graph? So just look down a line and you don't spell velocity. Here's the third one. If you have a velocity versus time graph, the area under the graph tells you the displacement. So I just want to show you an example of what that means. Let's suppose I have a problem. I got a hockey puck. It's sliding on ice. It's moving at 20 meters per second, and in 8 seconds it comes to a stop. How far does it go? Well, you could solve this problem. You could use the first equation and find the acceleration, or you have the acceleration, the initial velocity. You could use the first equation and find the acceleration, and then you could use the second equation and find the distance it travels, right? But if you graph velocity versus time, the area under the graph tells you the displacement, tells you how far it goes. So if you think about the graph, the area under the graph of the velocity versus time graph tells you how far it goes. So what is the area of that triangle? Well, it's 1/2 the base, which is 8, times the height, which is 20. 8 times 20 is 160. Half of that? 80. It goes 80 meters. That's it. So velocity versus time graph is helpful, not only because it helps you visualize what's going on in the problem, but the area under it tells you how far you've gone. Okay? And if you work it out, find the acceleration, and do all that stuff, you'll get the exact same answer. Okay? So that's just an important idea. We're not going to spend too much time with it, but finding areas under graphs is generally complicated. It requires calculus. Unless the graph's a straight line, and then you can find it using rectangles and trapezoids and triangles. All right, so Aristotle, ancient Greek philosopher, long time ago, like before the birth of Christ. Galileo was a philosopher slash scientist in the beginning of the Renaissance, right? Aristotle claimed that objects fell to Earth with a speed proportional to their mass. So things that had more mass fell to the Earth faster. That's what Aristotle said. And everybody believed him. His evidence was that a rock falls faster than a feather. Makes sense, right? Galileo came along and he said, hey, objects all fall to Earth at the same rate. So he did some experiments, and for example, 2 rocks with different masses would fall at the same rate and hit the ground. So who's right? What's wrong with Aristotle?
The feather would get drift and air under it.
Yeah, so a good example of something that is featherish is a coffee filter. And so you might say, well, a coffee filter will fall slower than a tennis ball, right? I better go back up here. There's supposed to be videoing this for people who are out. A coffee filter will fall faster than a tennis ball, right? Yeah? They're going to fall the same rate, Cameron?
Well, that one will get air under it.
So which one's going to hit the ground first? So the tennis ball will accelerate more than the coffee filter. That's what you're saying, right? Is that because it has more mass?
No.
Why is it?
Resistance.
Of what?
Air resistance.
There. So to check the mass hypothesis, I will keep the exact same amount of mass. I'm not making anything go away, right? The same mass is still in the coffee filter, and they'll fall at the same rate. So it's not about the mass. It's about the fact that if it's really light and it's big, then air resistance becomes a significant part of the problem, right? And it kind of floats and drifts. So Galileo is correct. Objects with different masses fall at the same rate. But Aristotle correctly noted that really light things that are also big fall at different rates. So the problem is that air resistance complicates it a little bit. So we are going to make the following caveat. If objects are not too big and are not moving too fast, they all fall at the same rate on Earth. Now, if we sucked all the air out of the room, right? It'd be a cool experiment. We'd all have 30 seconds to live, but while we had those 30 seconds, we could drop coffee filters and rocks and they would all fall at the same rate. And that experiment has been done. They can evacuate chambers, and you can go to YouTube and watch videos and stuff. But a feather falls at the same rate as a rock if there's no air. So when I say not too big and not too fast, if we throw you out of an airplane, you will accelerate downwards for a while, but eventually the air resistance up on you will be just as big as the force of gravity down on you, and you will stop accelerating. You will reach your terminal velocity, okay? And then hopefully you've got a parachute so it ends nicely. But that's what I mean by not too big, not too fast. So for most typical objects that aren't feathers and coffee filters, falling from heights that are less than 100 feet or so, all things fall at the same rate. Okay, so we kind of did that outside. We dropped different things and they all fell at the same rate, right? So I hope that's not a big surprise to you. We're going to skip the movie because we went outside and did it. So both accurately describe special cases. The problem is the air resistance. So if objects are light and large, air resistance is a problem. Or if they're moving fast, air resistance is a problem. Okay? So if they're not too big and not too light and not going too fast, we're going to ignore air resistance. Okay? So we can't really solve problems of skydivers yet. But for most things that are dropped from bridges and buildings and stuff, we can solve those kinds of problems. Okay? All right, so what you found in lab, I think, was that the distance an object falls is proportional to the time squared. You got a straight line. Your slope was the same slope for the tennis ball and the croquet ball, pretty much. Okay? So I think that's what you did in lab. So what that means is that if something falls twice as long, it goes 4 times as far. If a rock falls for 1 second, it goes 5 meters. If it falls for 2 seconds, how far does it go? It'll go 20 meters, right? 2 squared, 4 times as far. If it falls for 3 seconds, 3 times as far, 3 times as long, so 3 squared, 9 times as far. It'll go 45 meters. Okay, that's the idea. So if the distance an object falls is proportional to the time squared, so that's how we write it mathematically, then if the time is 1 second and it falls 5 meters, then if you fall twice as long, it goes 4 times as far, or 20 meters. In 3 seconds, it'll fall 45. What about 4 seconds? If it falls 4 times as long, it'll go 16 times as far, or 80 meters, okay, or 80 yards. So it keeps going faster and faster, all right? Okay, so for our equation, you guys look at your toolbox. Does that equation look familiar? It's got a tweak on it, though. What is the difference?
Y.
Yeah. When we solve problems up and down, things that are falling, we tend to use y instead of x. We use x for horizontal problems, right? Just like you do in math. X is a horizontal translation, y is a vertical translation. So that's our old equation from before. If an object is accelerating, its position, the distance it moves, can be described by this equation. And if the initial velocity is 0, that goes away. So if it starts from rest, the distance an object moves is 1/2 the acceleration times the time squared. So, in lab, your slope was about -4.9 or -5. If you compare this equation to this equation, what do you think the acceleration of the falling object is? If the slope, let's say -5, is half the acceleration, what's the acceleration? Right? Yeah, close to -10, right? So it turns out that if you compare those two, the distance the object fell, the time squared, the slope of our graph is half the acceleration due to gravity. So that means the acceleration is about -9.8. So this should be in your toolbox, I think. It's the last equation there. Is it even in your toolbox? Did I put it in there? Chapter 1. Yes, okay. When gravity is the only force acting on an object, it will accelerate at about -10 meters per second every second. Okay? When we do calculations, we use -9.81. But when we're just thinking about it in our heads and doing like thought problems, we use -10. Okay? Pretty close. So, the acceleration due to gravity. When gravity makes something accelerate, it changes the velocity of that thing 10 meters per second every second that it gets to pull on it. Okay? So, free fall is when gravity is the only force on an object. It's a little confusing because if I take a marker and I throw it upwards, when it leaves my hand, even when it's going upwards, it's in free fall. Because the only force on it is gravity. Okay? And so gravity causes the velocity to decrease 10 meters per second every second. Okay? This number is so important in physics, it gets its own letter. It's little g. We don't use little g for anything else. We don't use it as a variable. So it's a reserved variable. It's a reserved letter. We do this all the time. For example, have you ever seen an equation written like this? 3 pi equals 17. Solve for pi. Have you ever used pi as a variable? No, it's reserved. It's the ratio of the circumference to the diameter, right? It's so important in mathematics, mathematicians don't use this thing for anything else, right? We can use x for an unknown everywhere, but we never use pi. Physicists never use g for anything. It's acceleration due to gravity, okay? So g is just 9.81 meters per second squared, and because gravity acts downwards, the acceleration due to gravity is negative g. So g is just a positive number. All right, so an object is in free fall when the only force is gravity. So let's just do a little thought experiment here. If I throw a ball upwards at 30 meters per second, when it leaves my hand, it's going 30 meters per second. Okay? What will happen after 1 second? What will it be doing? So I'll make a little table here. This is the time, and this is the velocity. At 0 seconds, when I let go of it, it's going positive 30. This is meters per second. What will happen after 1 second? It'll slow down. How much? About 10 meters per second. So it'll be going 20. What about another second? It'll be going 10. What about another second? Oh, problem's over? No, now it's at its height. It stopped going up. What's it going to do in the next second? It's going to come down. It's going to be going -10. And then -20. See, no matter what the velocity is, even if it's positive, it will decrease 10 meters per second every second. That's what gravity does. It slows it down if it's moving up. It speeds it up if you're moving down. But your velocity always decreases 10 meters per second every second that goes by. Okay? So, how long is this thing in the air, do you think? It takes 3 seconds to get to its highest point, and then another 3 to come back down.
2 minutes.
So about 6 seconds. 2 minutes?
Oh, I added that wrong.
So you're just looking. It takes 3 seconds to get to its highest point. When it stops moving upwards, it is at its highest point. Right? When its velocity is 0. And then it starts falling again. Okay? That's the idea. So that's what gravity does. So, we are going to use all the equations we've already been using, and we're going to solve all the problems we've already been solving with one small change. We get a freebie now. You don't have to ask what's the acceleration. You don't need to solve for the acceleration. If gravity is changing the velocity, the acceleration is negative 9.81. Okay? Always, every time, at least while you're on Earth. Field trip to Mars, maybe you have to do something different. Okay. For now, okay? So, a couple of notes. We're going to use all the same equations, except instead of x's, we're going to use y's, just to remind us that things are going up and down. Later on in the unit, we're going to solve problems where we take balls and we throw them horizontally, like that. Okay? And when they're flying this way, they're moving up and sideways and down and sideways, and we will have x and y's in our problem. Okay? So we're going to use y for how far it moves vertically. Okay? You'll be able to figure out what angle and how fast to shoot a water balloon to hit a target. Second thing, free fall is when gravity is the only force acting on it, right? It's not in free fall while my arm is pushing it upwards. It doesn't become free fall till it leaves my hand. When does the problem end? Well, if I say, hey, I dropped the ball, what's the final velocity when it hits the ground? Well, once the ground starts hitting it, something else is changing its speed besides gravity, right? So our problem's done. When we say when a ball hits the ground, what's the final velocity? We don't really mean when it hits the ground. We mean 1/1,000,000th of a second before it hits the ground, okay? Because as soon as it starts hitting the ground, something besides gravity is acting on it. And so you need a whole new set of equations and a whole new force, which we don't have yet, okay? So the point is, don't assume that when you drop a ball, don't assume the final velocity is 0. If you drop a ball, gravity does not pull it to the ground, and then gravity doesn't make it stop on the ground. It's something else making it stop. So our problems, the final velocity is never 0. Okay? So here's my 2 example problems. I drop a rock out of a window that is 35 meters high. Do you guys have any idea how high 35 meters is? Anybody been to the, anybody a diver? Dive? No? No, like jumping off the diving board diving, you know.
Isn't that like 3 meters?
Yeah, that board's 3 meters, 10 feet, okay? Olympic high dive is 10 meters, which is 30 feet. So 35 meters is 100 feet. It's pretty high. It's not any buildings in Newtown, okay? It's probably like, you know, the ladder at the fire station on the biggest fire truck all the way to the top, okay? It's pretty high. So if we drop a ball from 35 meters up, so we're talking maybe you live in the city and you drop a ball out a window, how long does it take to reach the ground and how fast is it going when it gets to the ground? That's the question I want to answer. So what do you start with? Give it away. Let's start back there. Carly, what do you start with? What do you do first on your blank page when you get a new problem? Help her. Caitlin? You make a diagram. Yes, make a diagram. Okay. Make a picture of what's going on. Okay. What do you do next? Caitlin? You make your variable list and make it empty. Just write down the 5 variables. The only change is if it's a free fall problem, we're using y instead of x. All right, Grace. What is delta y? How far does it move?
35 meters.
Okay, almost. Trick question. It went from here down to the ground. What direction would that 35 be? Yeah, so we're going to need that negative later on. So we're going to say that the delta y, the distance we travel, was negative 35 meters. Does that make sense? All right, what is the initial velocity? Maddie? How do you know? Are you just hoping? Are you just hoping? What word tells you it's 0? There's one word up there. Liam? Dropped. When I say I dropped the ball, if I did that, what would I say? I threw it, right? Dropped implies we release it from rest, okay? So the word drop means it's released from rest, the initial velocity is 0. So Maddie's right, it was dropped, the initial velocity is 0. The final velocity is not 0. Gravity does not cause it to get to the ground and then stop. Something else causes it to stop, not gravity. So our problem is only about gravity. So we don't know that. Here's the freebie, guys. If gravity's changing the velocity, you know the acceleration. You don't need to solve for it. Makes your life easier. And we want to know how long does it take, the time, and we want to know how fast it's going. So look at your equations. Got an idea there, Evan? Which equation might you solve if you want to find the time? I'll give you a hint. We don't know the final velocity. Which one doesn't have final velocity?
Second one.
The second. We're going to solve the second one for t. Now, the warm-up tells me that you guys had a little trouble with this. Okay? I think half of you ended up getting it eventually, but manipulating an equation and solving for t was a little bit tricky, just mathematically. So I just want to go a little slow here. If I'm trying to solve for t, I got to get t by itself. It's there and there. Here it's squared, here it's linear. Because the initial velocity is 0, this entire term goes away. Don't cross off the v and leave the t. They're multiplied, it goes away. So I get this equation. If I want to solve this equation for t, the first thing I would do is multiply both sides by 2. You can divide both sides by 2, but you're going to end up with a compound fraction mess. Okay? The easiest thing to do is to clear the fraction. So multiply both sides by 2. If you multiply this side by 2, you'll have 2 delta y equals at squared. Then divide both sides by a. And then, how do you get t by itself? Take the square root. Okay, so t will be the square root of 2 times delta y over a. And that's a lot easier than delta y divided by a half divided by a. So then you're not sure what's divided by what, it's a compound fraction, right? Okay, plug in your numbers here. You get 2 times negative 35. And here's where it's important that the negative, you remember it. Because if you don't have a negative there, and you have a negative there, you're going to get a negative under your radical, and you can't evaluate that, right? So if you get a negative under the radical, don't just pretend it's not there. Figure out what you missed. It shouldn't be there. Plug in the numbers, and you get 2.67 seconds. It takes 2 3/4 seconds, or 2/3 seconds to fall. Okay? All right. What would you do now to find how fast it's going before it hits the ground? Eli? We now know the time. Which one? Which equation? Yeah, you can evaluate the first equation to find the final velocity. The initial velocity is 0, so you have 0 plus negative 9.81. There's a point there, you can't see it. Oops, sorry. 9.81 times 2.67, and you get about negative 26 meters per second, or about negative 60 miles an hour. Why is it negative? Because it's going downwards. Its velocity is heading down. Okay? So these are the exact same kinds of problems we've already solved, right? You just get a freebie. You know the acceleration. So that's one less thing you got to do. All right, another one quickly. If you drop a rock over the edge of a canyon and it takes 3.6 seconds to hit the ground, how high are you? So what are you going to do first? Make a diagram. Make a variable list. I'm going fast here. We're going to fill out our variable list. The time is 3.6 seconds. Delta y is unknown. The initial velocity is 0 because it's dropped. The final velocity is unknown, and there's our freebie. So what equation are you going to solve? Oh, we know the time. What equation are you going to solve? Zoe? First, second, or third one? We're trying to find delta y. Second one. You don't even have to solve anything, right? Because you already know the acceleration. You're just going to evaluate it. The initial velocity is 0. Plug in your numbers, and you get negative 64 meters. It says, how high is the student above the floor of the canyon? How can that be negative?
Because that's the rock going down.
What?
That's because the rock is going down.
Yeah. Delta y tells you how far the rock moved. If the rock goes 64 meters down, then the canyon or the bridge, whoops, I've switched problems. The canyon is 64 meters high, okay? So when you get negatives, don't just erase them and pretend like they're not there. Just think about what they mean. Maybe something should be negative. This is the distance the rock moved. It fell 64 meters, and so the canyon is 64 meters high, okay? Does that make sense? All right. I'm not gonna do that one. So, you've got another problem set to start chewing on. Okay, so you got about 15 minutes here. You can get started with the next one. The plan is to do a little review, a couple of activities next week, and have a test next Wednesday. Okay, so I'll give you a practice test and a review to practice on Tuesday. We'll do some stuff with graphs. We're finished the unit. That was it. What? The big day, whatever day I have you for an hour and a half.
That'll be Thursday.
That's Thursday?
Wednesday we are learning.
Oh crap.
Friday.
No,
No, we don't have that.
it's Thursday. And then Friday's odd days. That's right. All right, it'll be Thursday then.
What a shame.
Okay.
You love being in meetings all day.
I love being in meetings all day. All right. Make good solutions.